Save a little bit of time by saying that the next speaker, Owen Gingerich, is an extremely famous person who needs no introduction. Just for me.
90 years ago, when the Royal Astronomical Society was celebrating its centennial, the RAS president, A.S. Eddington, selected 6 great landmarks of astronomical progress in that century. He included the determination of stellar parallax, the discovery of Neptune, the rise of spectroscopic astronomy, and, from the decade of relevance to our conference, the measurement of the angular diameter of Betelgeuse with Michelson's interferometer. How astonishing to have this last item on the list, a measurement now so obscure that most of today's astronomy graduate students have never heard of it. Seems to me, Eddington declared, to be worthy of a place in this select list as a triumph of scientific achievement which is second to none. While today we may be reluctant to include this measurement in such a list, it behooves us to parse its meaning a bit more to place its significance in the astronomical ferment of the teens of the 19th century, the 20th century, the time of Lowell, Slipher, Harlow, Shapley, Russell, Curtis, Hertzsprung, Eddington, and Chapmans, to name a few of its leaders. In 1897, in volume 28 of the Harvard College Observatory Annals, Antonia Maury and Annie J. Cannon had presented the first fruits of their spectral classification work. Annie Cannon's scheme was a refinement of the letter categories started earlier by Wilhelmina Fleming under Pickering's general supervision. Cannon added the numbers so that classes G0, G1, G2 in principle followed A8 and A9, although not all the numbers were actually defined. This was to become the basis of the Henry Draper catalog, issued in, issued in volumes 91 to 99 of the Harvard Annals from 1918 to 24. Maury's scheme had 22 categories designated with Roman numerals, each with 3 subdivisions, A, B, and C. Too complicated and clumsy for widespread use, most astronomers concluded. The Danish astronomer Eijnar Hertzsprung, then working in Leiden, thought otherwise and wrote to Pickering in 1908 that, quote, "In my opinion, the separation by Antonia Maury of the C and AC stars is the most important advancement in stellar classification since the trials by Vogel and Secchi. To neglect the C properties in classifying stellar spectra, I think, is nearly the same thing as if the zoologist who has detected the deciding difference between a whale and a fish would continue in classifying them together." In any event, Maury's classifications enabled Hertzsprung to make an interesting analysis in 1905. What he showed was that the rare 36 stars in Maury's subclasses C and AC seemed intrinsically brighter than those in classes A and B. This should be seen as a peculiar and provocative result by the astronomical community. It should have been, except that not many saw it. Hertzsprung had buried it and his follow-up paper of 1907 in a journal for photographic technology, Zeitschrift für Wissenschaftliche Fotografie. Some years later, when Eddington found it, he chided Hertzsprung, saying, "One of the sins of your youth, to publish important papers in inaccessible places." It must have taken a few decades for the physical reasons for the subclass C characteristics to be understood. The normal diffuseness of the hydrogen lines in B, A, and F stars is caused by the Stark effect, enhanced by the comparative density of main sequence stars. Giant or supergiant stars have much lower particle densities in their atmospheres, so the atomic excitation levels are much less disturbed, and the spectral lines are distinctly sharper. Note that Miss Mallary classified 649 brighter stars, northern stars, in her monograph, of which only 35 were labeled C or AC, all in spectral types that showed conspicuous hydrogen lines. All right, I just show you that Hertzsprung and Russell got together at the International Solar Union Conference in Bonn, and Russell always stands out in these pictures by his wonderful way of parting his hair right down the middle. In a third paper, printed in the Potsdam Astrophysical Observatory publications, Hertzsprung actually included diagrams plotting apparent magnitude against color for stars in the Pleiades and Hyades. Because the stars in each cluster could be assumed to be at the same distance, this was equivalent to plotting the absolute magnitude against spectral time. But the Pleiades cluster has no supergiants or giants, so its diagram showed no bifurcation. In contrast, a few giants, scarcely even a handful, were present in the Hyades, once again showing a twofold division of stars within their spectral types, but hardly dramatically so. So you can see a main sequence here and a few giant stars there. This is plotted against effective temperature of the atmosphere. No. This has got to be color across here. So it is in some way, can't be effective temperatures. It's going the wrong way. Anyway, it's got to be connected somehow with the color. Several years later, in 1913, Henry Norris Russell could demonstrate the effect far more strikingly, because by that time he had access to the parallax for many stars, and thus he could plot absolute magnitude against spectral type with a substantial number of points. Russell distinguished the stars into dwarfs and giants, attributing the nomenclature to Hertzsprung, who had, in fact, not used such a designation in either of his Zeitschrift papers or in the Potsdam publication. Many years ago, I directly queried Hertzsprung about his possible invention of the dwarf-giant nomenclature, and he replied as follows: I hasten to say that I have avoided the expressions giant and dwarf because the stars are not very different in mass, but in density. They are more or less swollen. So it's quite possible that Russell himself invented the usage. This nomenclature was promptly picked up by the Observatory magazine by entitling Russell's report to the June 1913 meeting of the Royal Astronomical Society, Giant and Dwarf Stars. Russell and several other American astronomers had stopped in London on their way to the International Solar Union meeting in Bonn. The RAS session gave Russell a much larger audience than at the Astronomy and Astrophysics Society of America meeting in Atlanta at the end of the year. You pick out Russell pretty straight away. He's the only one who parts his hair in the middle. Subsequently, he published his paper with the diagram in Popular Astronomy and in Nature. The earlier observatory report noted that there had been slides but didn't reproduce them. For the moment, it's enough to notice that much of astronomy was in flux in this decade, from the source of stellar energy and its relevance to stellar evolution, to the place of the spiral nebulae and the structure of the Milky Way. An unexpected discovery by Chapmans, announced in 1904 at the St. Louis World's Fair, of star streaming indicated that the motion of the stars in the Milky Way was not random. The physical basis for this effect would not be understood until Shapley's model of the Milky Way would provide a basis for the knowledge of galactic rotation. But star streaming would provide a central focus of Eddington's first book, Stellar Movements and the Structure of the Universe, published in 1914. And the book was one of the earliest presentations of Russell's diagram. Russell had displayed his diagram to the crowded meeting of the Royal Astronomical Society in June of 1913, and soon thereafter Eddington had asked Russell for a copy. It played an important role in the chapter where Eddington related stellar movements to spectral classes. In his book, Eddington wrestled at length with the observation that the early type stars had distinctly smaller space velocities than K and M stars, and this was after removing the effects of solar motion. Ultimately, it became an issue of luminosities. In the parallax work, M stars were the least luminous, whereas in the radial velocity work, the stars were systematically selected by magnitude, since brighter stars were more congenial to spectrographic analysis. And this picked up more highly luminous stars, stars that we now know to be giant stars. The leading contribution to this problem, Eddington wrote in his book, was in the final stage, which was in its final stages of preparation when he had heard about this, is the hypothesis of giant and dwarf stars put forward by Hertzsprung and Russell. They consider each spectral type to have two divisions which are not in reality closely related. And there in his book, across from that paragraph, is a typographically very clean rendition of the diagram that Russell had sent him. This was the beginning of the resolution of Eddington's stellar motions paradox, but it would require both the knowledge of galactic rotation and of stellar populations before the puzzle would really be resolved. For Russell, the diagram provided a convenient way to illustrate his ideas about stellar evolution. In introducing his diagram, he noted that the stellar densities increased from the giant branch down the dwarf sequence. That is what we call the main sequence. Quote, "If that is also the order of advancing age, we are led at once back to Lockyer's hypothesis that a star is hottest near the middle of its history, and then the redder stars fall into two groups, one of rising and the other of falling temperature." So this is the diagram which is from Lockyer's work on the meteoritic hypothesis. And you can see that the stars are red here as they go up, get their hottest when they're A and B stars, and then cool back down again. Of course, Eddington's mass luminosity relation would destroy this evolutionary march up the main sequence. But that would come a decade later. Russell's original idea of cool, newly formed stars moving up the main sequence as they became hotter was abandoned when Eddington demonstrated that the main sequence was essentially a mass sequence. The stars had to move down the main sequence as they gradually lost their active mass. So here you can see the stars coming in from the giant branch, red ones getting hotter, and then as they lost their mass, they went down the main sequence, and now for the first time you have a white dwarf star included within the same kind of a diagram. This diagram comes from the classic 1925 Russell, Dugan, and Stewart textbook, and for the first time, as I just indicated, and includes a white dwarf in the evolutionary track. I think Russell could hardly have imagined at that time what a powerful evolutionary tool his diagram would eventually become in the hands of Bada and Schwarzschild and their students, including Sandage, Arp, and Baum. The issue of the naming of the diagram smoldered for years. This visual tool was for 3 decades generally referred to as the Russell diagram, although in 1933 Bengt Strömgren introduced the designation Hertzsprung-Russell diagram, abbreviated H-R, in a paper in the Zeitschrift für Astrophysik. Although in his famous paper there on the hydrogen content of stars, he had in the previous year used Russell diagram. In the 1940s, it was renamed the HR diagram on the style sheet of the Astrophysical Journal. This done by co-editor Chandrasekhar to satisfy the relentless hectoring from fellow Chicago faculty member Gerard Kuiper. Chandra, however, had already adopted Strömgren's designations with a chapter headed Strömgren's Interpretation of the Hertzsprung-Russell Diagram, and the use of the abbreviation HR within the chapter itself in his 1939 book entitled Stellar Structure. But meanwhile, back in the 19-teens, the general concept of dwarf and giant stars was essential in the galactic structure work of Harlow Shapley, Russell's first graduate student, now transplanted to Mount Wilson Observatory. His Princeton thesis had included observations and analysis of 90 eclipsing binaries, essentially raising the number of binary star orbits by an order of magnitude. Now, with the 60-inch reflector, he could attack the problem of variable stars in globular clusters. And this led to the calibration of Henrietta Leavitt's period-luminosity relation. Since none of the field Cepheids in the Milky Way were close enough for trigonometric parallaxes, Shapley was obliged to fall back on statistical parallax, using the proper motions of 11 Cepheids, which is a pretty sparse sample. Here's where the insight provided by the Russell diagram became critical. The brightest stars in the globular clusters included Cepheid variables and yellow K stars. Shapley recognized that the yellow K stars were giant stars, whose absolute magnitudes were approximately known from giant galactic field stars. This credentialed his calibration of the period-luminosity relation by showing that the calibrated luminosity of the Cepheids was comparable to the luminosity of the K giants. In the celebrated Shapley-Curtis National Academy of Sciences debate held in Washington in April 1920, Shapley exhibited his calibrated period luminosity diagram, beautifully and unbelievably smooth, by averaging triplets of the basic set of 11 Cepheids and then adjusting their absolute magnitudes. Because Shapley firmly believed that a physical law connected the pulsation periods of these stars and luminosities, he felt that the procedure was fully justified. One of the things he had done as part of his Princeton work on the binary stars was to show that if a Cepheid star was a binary star, which was the standard interpretation at that time, one component had to be inside the atmosphere of the other one. And so there arose the idea of the pulsation hypothesis, that these were physical stars and therefore the physical period depended on the nature of the star itself. That this avant-garde technique of statistical parallax was not acceptable to everyone is readily seen from Heber Curtis's riposte, published in his contribution to the debate. His plot of the period luminosity diagram looks like the target of a beginner marksman, essentially a scatter diagram. His diagram suggests that he didn't believe in the period luminosity relation. In the revised post-debate version of the 1920 encounter with Curtis, Shapley pushed back, saying, "An argument much insisted upon by Curtis is that the average absolute magnitude of stars around the sun is equal to or fainter than the solar brightness. Hence, the average stars we see in clusters are also dwarfs." Or to put it in a different way, he argues that since the mean spectral class of a globular cluster is that of the solar type, and the average solar type star near the sun is of solar luminosity, the stars photographed in globular clusters must be of solar luminosity, hence not distant. This deduction, he holds, is in compliance with proposition C, uniformity throughout the universe. But in drawing the conclusion, Curtis apparently ignores, first, the very common existence of red and yellow giant stars in stellar systems. And second, in treating a distant system, we naturally first observe its giant stars. Suppose that an observer, confined to a small valley, attempts to measure the distances of surrounding mountain peaks. Because of the short baseline allowed him, his trigonometric parallaxes are valueless except for the nearby hills. On the remote peaks, however, his telescope shows green foliage. First, he assumes approximate botanical uniformity throughout all visible territory. Thus, he finds the average height of all plants immediately surrounding him, conifers, palms, asters, clovers, and so forth, is 1 foot. Correlating this average height of all plants visible against the skyline on the distant peaks, he obtains values of the distances. If, however, he had used some method of distinguishing various floral types, he would not have mistaken pines for asters and obtained erroneous results for the distances of the surrounding mountains, unquote. This critical understanding, then, depended on the efficacy of Russell's dwarf and giant distinction. It's well known that in 1920, Shapley did not believe in the cosmological distances of Curtis's spiral nebulae. It's not so well known that in 1920, Curtis failed to appreciate the significance of the Russell diagram for understanding the large size of the Milky Way and the key role of the period luminosity relation. In 1921, when Hubble found his first Cepheid in M31, it was to Shapley that he wrote for the calibrated period luminosity curve. 1924, he's getting ready to actually publish about it, and this is Hubble's letter to Shapley saying, "Can you give me any late advice on the photographic period luminosity curve for Cepheids?" So it was Shapley's calibration that Hubble used to get the distances. Within just a few years, both Shapley and Curtis fundamentally changed their views concerning the size of the Milky Way and the nature of spirals. In 1966, I took my English colleague, Michael Hoskin, for an oral history interview with Shapley. And we found that the 81-year-old astronomer could scarcely even imagine a time when he thought spirals were not distant galaxies. Tempus fugit. Beware of oral history interviews. I think you recognize Shapley, Hertzsprung, and Kuiper, picture I took in the 1958 IAU meeting in Moscow.
Great. Questions, please?
Just a comment about Eddington, of course. Naturally, he would think very highly of the Michelson measurement because he was the one who predicted it. Let
Okay.
He specified the actual angular diameter that they needed to move the mirrors back and forth and to achieve the null result on the interferometer. Couldn't have done it without that prediction.
Yes.
I was interested in, and perhaps you could speak a little further to this. It seems then that translating the period luminosity law that Henrietta Leavitt discovered to actually being a practical standard candle was a little more complicated because you couldn't use trigonometric parallax at the time. Or do I understand that correctly?
That's right. She could get this relation because it was done from the small Magellanic Cloud. And so you could assume that all of the stars were of the same distance, essentially, and therefore when you plot them, you would get the relationship. But it wasn't useful at all for finding the distances to other isolated Cepheids or Cepheids in globular clusters. And so it required this kind of leap to use 11 Cepheids. He was very careful in his choice of them. He threw out one of them, for example, because the light curve didn't look right, and it was what we would now see as a W Virginis star, population 2 star, and it was good to eliminate it from the set. The problem was, of course, that the set that he calibrated did not link correctly with the cluster type short period variables, which are so abundant in the globular clusters. So his distances and his size of the Milky Way was then prejudiced in being substantially larger than it actually is because of, and that didn't get sorted out, of course, until the work of Bada on the populations.
Can you describe if there was any tension involved when, as you said, the Russell diagram was renamed the Hertzsprung-Russell diagram? Was that Chandra Sekhar who did that? Or?
Well, I'm sure that it brought it about with Chandra doing that for the style sheet of the Astrophysical Journal. I can remember being a reader of Sky and Telescope, let us say, in the 1950s, that Russell diagram would still appear in print there.
We still have time for one more question or something like that. Right.
I've been reading some of these papers just before the Great Debate, and I know that Curtis and Shapley both had some ideas that the novae they were measuring in the spiral nebula appeared to be quite distant compared to the galactic nebula. Can you touch on that at all?
Well, Shapley, in one of his papers, did give a distance of 1 million light years for the Andromeda galaxy, but he backed off of that because of S Andromedae, the supernova, which threw a great monkey wrench into this kind of determination. Also, of course, these proper motion measurements of Van Manen, and he said, well, Van Manen was my friend at Mount Wilson, and so I didn't want to just reject his results.
But Curtis also has a paper where he measures the novae, and he also gets similar. Well, Curtis also had a paper around the same time as Shapley with similar results using novae, but you don't have anything to say about that? No.
That's right. No, this was a popular time to find novae. It was done by various people. Curtis got a bunch of them, and there were some being found at Mount Wilson as well. So it was very ambiguous. But now you must say Shapley not Shapley.
Shapley.
It was misspelled in the previous paper. If you're going to give that talk again, that's, make that typo correction.
So you think that this supernovae made the big difference because also Lundmark and this guy Gudlau Janssen and Haar, they also published papers with these novae in these external, these spiral nebulae with this idea that they were external. Maybe they weren't so beholden to Van Manen's friendship, or maybe they didn't believe this.
Well, you see, by Shapley having such a large Milky Way galaxy, he figured that the Kapteyn universe, which was very much smaller, was just sort of like a local distribution, and he called the Milky Way, he later wrote a paper on it as being a super galaxy made up of lots of maybe smaller parts. What we think of as Shapley's great spiral galaxy with the nucleus and so on came in the 1930s with Plaskett's diagram of how it would be laid out. So the picture that Shapley had of it in 1920 was rather different from what we see later and think about being related there. So, but once he had that big size and he saw that the spirals were not found in the Milky Way at all, and therefore their distribution seemed to be very carefully linked to the Milky Way. And so it seemed natural to him that they could be some sort of outliers to the Milky Way system as it was seen. So it wasn't totally crazy to think that the spiral galaxies were local.
Okay, I think we better press on. It's like opening